speaker is Zavadski. His report is devoted to averaging of operators in groups and properties of its generators.
Is averaging of operator semigroups and properties of its generator. My talk is mainly about operator semigroups. I wish to define different relations on infinite dimensional spaces because it is important to investigate complex quantum infinite dimensional systems. Okay. Firstly, I will say some words about measure theory on infinite dimensional spaces and construct some operator semigroups which consists of shift operators. I will investigate which conditions should be satisfied in order to fulfill continuity in or more precisely strong operating continuity in strong operating topology. And after that, I will average these operator semigroups by some Gaussian measures and analyze the result. Subsequently, different populations will be generators of obtained semigroups. And like in finite dimensional case, different populations will be sum of partial derivatives. That is why I will tell some words about smooth functions on infinite dimensional spaces. It is well known that there is no way to construct an analog, that there is no way to construct analogous measure on infinite dimensional spaces. That is why we have to sacrifice some of its main properties. For example, I wish to build a lambda which is sigma additive and shift invariant. As an example of a space, we take the space L infinity, and I will briefly discuss how this measure was constructed. Let's take a cube K, which is equal to this product 0, 1 multiplied by 0, 1 and so on to infinity, and define a product measure lambda. It is a well-defined measure on this cube, and our next step is to extend this measure on shifts of different vectors from the space L infinity. For example, we take a measurable set A and shift this set on a vector H, and we say that lambda of H plus A is equal lambda of A. Maybe I should write this.
Yes, please.
Means if you have a measurable set A, we consider a shift of a set A across a vector H and obtain a measurable set and extend a measure lambda on these shifts in this natural way. This is the unique extension because we require invariance with respect to shifts. And after that, we use the Taylor scheme in order to obtain a sigma additive measure on the whole space. As a result, we have a theorem. Measure lambda is well defined, sigma additive and shift invariant on beta from L infinity. We consider the moral sigma algebra with respect to topology of pointwise convergence. Our next step is to consider different shift operators. Let's define operators ATH from L2 to L2 in the following way. It is a shift of the argument. It is easy to see that these shifts form a semigroup, and norm of each operator is equal to 1. Also, there is a question when these semigroups will be strongly continuous? The answer is the theorem. An operator semigroup ATH is strongly continuous if and only if H belongs to the L1 space. Our next step is to average these different operator semigroups ATH by a random parameter H, but we know that these semigroups are strongly continuous if and only if H belongs to L1. That is why we need to build a distribution which is concentrated on the space on the L1 space. It leads us to the following problem. We need to build a Gaussian measure which is concentrated on the L1 space. To do it, we need two different objects. The first object is a sequence AN from 0 to 1, and this sequence must satisfy the following condition. Infinite product must be bigger than 0 but less than 1. And the second object is a vector H which belongs to L1 and each coordinate is bigger than 0. To construct the Gaussian measure, we need to choose a sequence sigma n, a sequence of deviations. And we do it in the following way. Our sigma n must satisfy this equation. This equation always has solutions, and we take the solutions of this equation. And Gaussian measure mu, which is equal to infinite tensor product of Gaussian measures gamma n, which gamma n is a Gaussian measure which corresponds to deviation sigma n. Sigma n was formed from this equation. A measure mu is well defined on Borel sigma algebra in space R infinity with respect to topology of point-wise convergence, and the restriction of mu to the L2 space is a centered Gaussian measure. Let's see that mu depends on a sequence AN and a vector H. So we build many different measures of mu. And we have the following lemma. For every mu from M, mu is concentrated on the L1 space. It is important because our shifts, our semigroups of shifts are strongly continuous if and only if shifts belongs to the space L1. Our next step is to average these shifts by a random parameter H, whose distribution is given by the constructed Gaussian measures mu. It is interesting to note that we can't just write this expression ht u from x equals the following integral, because this integral in some cases isn't a measurable function by x. Why it happens? It happens because our measure lambda isn't sigma-finite. That is why we can't just apply Fubini theorem, which guarantee at least measurability of this integral. But we can define this integral in the following way. We can define it as a Pepys integral. Let's see on this expression. We have two integrals and two different measures, mu and lambda. And we see that internal integration is actually not over the whole space L infinity, but we integrate by the support of function v. And we know that function v is L2 function. It means that it has sigma-finite support. I mean that support of function v can be represented as a countable union of sets with finite measure. That is why in this case we can apply Fubini theorem and we obtain that internal integral is measurable and subsequently the whole scalar, the whole dot product is well defined. And it is interesting to note that we obtain some function h from t, and this function actually is a semigroup. ht is a semigroup, and moreover it is a strongly continuous semigroup. It means that it has dense defined generator. This generator is actually our Laplacian. In finite dimensional case, it's true, it holds, and in finite dimensional case, we have representation of this operator. It's just a sum of partial derivatives, it's well known. But in infinite dimensional case, the situation is a little bit different. And to analyze smooth functions on infinite dimensional spaces, firstly we should define these functions. But we have another interesting fact. What about continuous functions? It is well known that in a finite dimensional case, continuous functions dense in the whole L2 space. What about infinite dimensional case? It was proved that even continuous functions have trivial intersection with the whole L2 space. It means if function f belongs to space of continuous functions on a space on the L infinity space with respect to pointwise convergence topology, and it belongs to L2, that it means that f equals to 0. And it creates additional problems and struggles. But there is a way how to deal with it. We can talk about smooth functions on L2 and how to define it. We define a class of functions called CL2 L2n, which consists of functions which are smooth by the first n variables. For example, we can consider product of functions from D on Rn and indicator functions and indicator function. It is easy to see that this function belongs to CL2N. Moreover, there is the theorem. The closure of CL2N is equal to L2. So we have a rich class of smooth functions, and that is why we can define the relations on these classes. And like in classical case, these functions are a domain of Laplacian. Also interesting to see that intersection of all CL2N classes, which consists of functions which are smooth by all variables, will be also dense in L2. And on this class, we can define different Laplacians. Because these constructions depends on this construction depends on the measure mu. And here, a measure mu depends on two sequences actually. That is why we subsequently define different Laplacians on infinite dimensional spaces. This is because there is no way to construct a very big measure there. So, moreover, what about these Laplacians? They are dense defined and they are self-adjoint. This is because they were obtained as a generator of good semigroups, and subsequently the spectrum is real, and like in finite dimensional case, we doesn't have eigenvectors of these Laplacians. And I think that that is the end of my talk. And you're welcome to ask me.
Questions, please?
You mentioned some measures, Gaussian measures, on A1. Many years ago, somewhere in Moscow, there existed a PhD student of Professor Schiller. His name was Mikhail Sonis, and he investigated just Gaussian measures on non-Hilbert spaces, like A1. Do you know, did you read any papers by Sonis on this subject? It's not very long.
Yes. I am familiar with at least some of these works, and Sonis consider general case. But in my research, it is enough to build a simple example, which is enough to build these Laplacians.
So your results are, I would like to say, complement each other.
Yeah, I think that's true.
His and yours.
Yes. Thank you for the question. Yes.
I have listened to your report, the previous version of your report on the conference of Moscow Physical and Technical Institute. Have you arranged the Hirota function on your measure? Have you performed my suggestion? Or yes or not yet?
Actually, no, because this function is a little bit strange, and I'm not sure that this function is measurable here.
Other questions?
Скажи, tell us please, could you give an example of one function that had compact support divided on L infinity, and you can integrate it with respect to lambda?
Okay. You know, it depends where you consider compactness. It depends on topology. What kind of topology do you mean?
You have beta there. B.
Yes, it's the
B.
topology of pointwise convergence.
Okay?
Okay,
You define a topology.
yes.
After that, you define the Borel set.
Yes.
So, we have topology. Isn't it? Therefore, we know what compact set means.
Yes, okay, I see. Also, there is the trivial answer. You may.
Zero.
Yes.
Thank you.
Okay. But also there are many different functions, like just a cube. We can take something like this.
Indicator function.
What is it? Let's see.
It means
Indicator function.
indicator function.
Индикатор. Индикатор куба.
Compact.
This is somewhat 0, 1 to the power of infinity, and it's compact.
It's compact.
Yes.
I know that it's not concentrated on compact.
Okay, I see. You know, actually.
Okay, I see. If you can do vast our time, so.
Okay, I'm listening about it.
Okay.
Yes, okay.
Let us thank physics again. Thank